Hello there. Today we're working through a full example to merit level of a linear programming exercise for NCEA level 3. Notice this worksheet is heavily scaffolded, has a bunch of steps in it. This will not always happen in the examples for NCEA, and in this particular case I'm going to add one extra scaffold as well, which is a step 0 in which we find the variables that we need to use in this equation. So we're going to start by doing that. It's usually a good idea to look first to any statement about the actual profit or cost and see if we can find the number that changes is essentially what a variable is here. So I'm looking through it and I find this statement: the profit on each Moa burger is $2.20 and each Weka burger is $1, and that tells me that this is probably our objective function, and furthermore that my variables should be the number of Moa burgers and the number of Weka burgers. So I'm going to start off by naming each of those. That variable is, and this one is y. So x is the number of Moa burgers, y is the number of Weka burgers. After that, then we do indeed go down to working out the inequations. It's actually broken it out for us to make it a little bit easier. Sometimes you have an inequation across multiple sentences. So we have this sentence: it takes 3 minutes to make a Moa burger and 2 minutes to make a Weka burger, but the total time available to make the burgers is 4 hours. And that enables us to see that there's some sort of connection between those two sentences. We could write out 3 minutes, 3x, plus 2y, 2 minutes per Weka burger, and some relationship to our total here. Note the units are in hours, not minutes, so we need to adjust those to be hours. So we're going to do 4 times 60 to give us the number of minutes, so that we're using the same units as we wrote here. So that will be 4 times 60, which is 240. And then we just have to work out whether it's greater than or less than here for the constraint. In this case, it says the total time available, which typically means that you could use less time. So that means this side here could be less. So we put the inequality that way around. Let's move on to, I'm going to number that equation as 1, 2 right now. The next one is the cost of the ingredients for each burger. Type of burger is $2, and the shop has only $200 available for ingredients. So once again, we'll get a 2-sentence constraint. We can model that as 2x, $2 times the number of Moa burgers, plus $2 times the number of Weka burgers, and something to do with $200. We just have to think, can it be more or less? It's only 200 available, so no more than 200, so this could be less. So we put the inequality that way around. This statement: the shop must provide at least 10 of each type of burger, can be written out as 2 constraints. So because each one is separate, so we're going to write firstly the number of Moa burgers and 10. Which way should it be? Well, it's got to be at least 10, so it could be more than 10. So x could be greater than 10, so put it this way. And the same goes for the y. The Weka burgers can also be greater than or equal to 10. We also have this one here, that it must be no more than 60 Moa burgers. Moas are the x's. Which way around? Well, it cannot be more. It can be less than or equal to 60, and same for the Weka burgers we have. Now let's make sure we've numbered all of those equations. Okay, now I'm just going to copy those equations down, because I'm going to next be drawing the graph of all of these equations, and I'd like to not have to be constantly jumping backwards and forwards here between them, so I'll do that. Okay, I've prepared one earlier here. I've moved all of those constraints down so they're a little bit easier to see for the drawing of the lines. We actually have a step before that to draw the axis, but you can see that in this example the axis has already been drawn here. In general, you would want to find the highest values, usually from the equations that have both variables in them, before you numbered off your axes for the choice. So you draw an axis straight away, you might find that most of your lines are off the graph. But we've been given them here, so the process of drawing them is quite straightforward. So firstly I'm going to draw number 1. I'm going to find the x-intercept by setting y equals 0, so I hide the y, and I've got 3x equals 240. I divide 240 by 3 and I get 80, which is here. And then same for the y-axis, I hide the x, set x as 0, 2y is 240, 240 divided by 2 is 120. Set that there, then draw a line between those 2 points. Draw it nice and long and label it as you go too. Do the same for the next one. 2x, so we're going to set y as 0, x is now going to be 200 divided by 2 is 100, and setting y as 0, x is 0, sorry, the same calculation on the other side for y will be equal to 100. So we draw lines connecting those 2 points. Go nice and deep so that you can label your lines and find them later on once you've started shading everything out. Line number 3, where x is greater than or equal to 10, it's going to be a vertical line because it has only x values in it. The y does not y is not changing in it. So we draw it nice and deep and label it. Same for the y is greater than 10. This is 20, so 10 is here. Label that as number 4. And then where x is greater than 60, put that line there. That's number 5. And y is greater than or equal to 80 is a horizontal line just here. And we'll label that one number 6. Okay, so that's drawing the lines. Now we need to know how to shade them out. And for that what we use is the point test. So we take a point that we know is not on one of the lines. We wish to find out which side of the line to shade. So we can pick, for example, line number 1, this line here. And this line here. And we can see clearly that 0.00 is not on that line, so we can use it to do the point test. We put 0, 0 into this function and see if this statement is still true. Recording managed to die there while I was explaining the point test, so I'll go over it one more time. Make sure it is recording. Yep. So what we're trying to find for the very first line, number 1 here, is does it satisfy the point test. So we pick this point here, 0, 0, put it in here into the line that makes 1, put 0 in here, 0 in here, we get 0 on that side and see if it's still true. So 0 times 3 plus 2 times 0 comes to 0. Is it less than 240? Yes it is, which means that that side, this side of the line number 1 is allowed, which means the other side is not, which is why we shaded it out there. We do the same for number 2. We put in 0 and 0, we get 0 is less than 200, is true, So this line here is saying that that point is allowed, which means the other side must be shaded out as not allowed. Now the line where x is greater than 10, we asked the question, is 0 greater than 10? 0 is not greater than 10, so that's not allowed, so we shade this side out, the opposite side. Same with the y. Same with the y. We check if this y value here, 0, is greater than 10. It is not, so this is not allowed, so we shade down there. And the other 2 points, x is less than 60. Is 0 less than 60? Yes, it is. So this is allowed by this particular constraint, number 5 here. So we shade out that side there. And then we have y is less than 80. Is y 0 for y less than 80? Yes, it is. So that would be allowed by this constraint going this way. So we shade off up that way, which in the end was only actually that little corner there left to shade. So that's us finding the feasible space, which I've labelled here. So what that means is that any set of x or y values inside this area here are allowed. They satisfy these constraints. They would be possible choices for burgers to make that don't violate any of the rules given above. Now our next concern is to find, well, which one is the best, which is the most optimal, and the theorem says that it'll always be at a corner, one of the vertices. So we end up identifying the vertices. I draw a circle around that one there, that corner there, that corner there, that one, and this one. So we actually have 6 corners in this particular example that could be potentially optimal solutions to this problem. Note there are some intersections of some of these constraints here that are not circled because they are in clearly infeasible space. One of the other constraints has made this point here, the intersection between number 4 and number 1, infeasible, and that would be this constraint here, number 5, for example, has made that point infeasible. X must be less than 60, so it can't be out here being 70. So we didn't have to circle these, we don't have to test those points, but these ones we do have to test, and we have to test all of them. Now notice on this side of the diagram, just move that across a little bit, on the side of the worksheet it actually says to find these 4 vertexes, because we don't know which one. There's possibly a slight mistake here. There's actually 6 to find, so I'm just going to put another couple of empty braces there for the other solutions, and we've got to work out where these are. For some of these it's a trivial problem. For example, that one there is the intersection of constraint 3 and 4. It's just at x equals 10, y equals 10, so we can write that one in there, 10, 10. This one here is pretty trivial. It's where 5 and 4 intersect, so that's x equals 60, y equals 10. This one here is where constraints 3 and 6 intersect. 3 and 6 are x equals 10 and y equals 80. So those are pretty easy. This one and this one are rather simple as well. They involve a small amount of algebra to be done. So let's find this one first. That's the intersection of number 1 and number 5. So we have this constraint and this constraint here, where x is 60. So we literally just put 60 into this equation here for x. 60 times 3 is 180, and we subtract that off. So I'm just going to do that. Have I got room to do the working on this page? Yes, I will. I'll do it here. So the critical point there will be 3, actually let's do that in green, 3 times 60 plus 2y equals 240, because this is x equals 60, and we now solve this. 240 minus 180 equals 60, and y is equal to 30. So this is our x and our y, 60, 30. Similarly for this point here, that's constraint number 6 intersecting with constraint number 2. So constraint 6 is y equals 80 or less than 80, and constraint 2. So I'm just going to do that little bit of working here. I'm going to go y is equal to 80, and we're going to put that into 2x plus 2 times 80 equals 200, and solve that. 2x is equal to 280 minus 160, which is equal to 120, so x equals 60. So we've got x is 60, y is 80, and we can put that one in here. And the very last one, the most difficult one of all, can be done using your calculator. Okay. I'll actually do it on the other side just briefly. 3x plus 2y is 240. X plus 2y is 200. And we'll solve that for x and y. This is a very straightforward one. This is an elimination. We can literally subtract one equation from the other, just making sure these are the right equations. So 3x minus 2x is x, 2y minus 2y equals nothing, 240 minus 200 is 40, and we've got our x value straight away. We can now put that straight back into either one of these. I'm going to use this one. So 2 times 40 plus 2y equals 200. 2y equals 200 minus 80 is 120. Y equals 60. So these are our two numbers. X is 40, y is 60. And I'm going to put that back into my found points. Just here. 40, 60, wasn't it? 40, 60, yes. And at this point, we've found the vertices of the feasible region. Here. These ones here. There were 6 of them, and we now have to move on to deciding which one is most optimal. Before I continue, I should point out there's a slight calculation error made earlier, that I wrote down 200 here as 280. I've corrected this, so this should have been 200 minus 160, which is 40, and therefore x is equal to 20, which I've put down through to here. In order to find the optimal one, we first need to actually work out what our objective function is. It was mentioned slightly earlier that profit on each mile burger is $2.20 and each wicker burger is $1 in the original problem, but that has also been written out here again, and that leads us to a pretty straightforward profit statement, which is that the profit equals $2.20 times x, and $1, or just 1, times y. And we're going to have to put every one of these points through this profit equation, putting 10, 10 into x and y, 60, 10 into x and y, and find the most maximal one. So I've just prepared this earlier, so that you're aware of what we're doing here. the equation there. 2.2x plus y is what I'm working out here, so 2.2 is getting multiplied all the way down, and then plus equals all the way down, and then I just substitute in the points in place of x and y in these functions here. So I've gone 10, 10 is 10, 10, 60, 60, 10, 10, 80, 60, 30, 20, 80, 40, 60. And I've worked these numbers out already, so we have, they're just calculated jobbies. It's really laborious and tedious, but has to be done, adding up all the values into this calculation. Just checking those are my actual values, 20 and 80, yep, cool. And we have solved our problem here. We have found, simply have to look down the list for the biggest number. 162 is the biggest number, so this is our optimal critical point, 60, 30. So x is 60, y is 30, which is this point here. And the very last step is, of course, you should state the maximum profit, which we found was 162. You should always answer a question like this with words. So, Murder Burger should make 60 burgers, which are what the X's are. And 30, you can probably use digits if you like, Wicker Burgers. For maximal profit. And there, people, is a problem of this type taken all the way through to an excellence answer. Not excellence, sorry, a merit answer. The excellence answer will generally involve something having to be done after finding this. So the problem will be altered in some slight way, and you may have to find more than one solution, or you may have to find an integer solution. It may not be at a round whole number point like 60/30 is. It may be fractional and you can't make half a burger, so we might be able to make half a burger, but there's other problems where it's a bit meaningless to halve the quantities that we're trying to optimize, and so you'll have to find points around that region. Just as an idea of what a quick way to always check your answer might be to draw an actual profit line. So you work out a point that's going to be in the region. Say, for example, let's try this one here, which is 30, 50, and we say 2.2 x plus y equals, and we put in the values, 2.2 times 30, plus 50 equals, work out what that is, 30 times 2.2 is 60 plus 0.2 of 30 is 66 plus 50 is 116. And then put this into the whole equation to draw a line. So and then you can actually find some answers here. Firstly, we'll hide where is the y-intercept. It's just at 116. I'm going to draw this in blue. 116 is about there. Mark it. And where is the x-intercept? It's at 116 divided by 2.2. Get my calculator. At 52.7, which is about here. It goes through that point, which is nice. We found the right point. And you can see from the slope of this line here that if we keep taking parallel lines like this with it and slide across like this, that the point we found is indeed the one that's the last to disappear out of the feasible space. So there it is. It would be $116 if they chose 30 and 50. We keep sliding the profit up until eventually we get to the maximal profit, which was 132. And it tells us how many burgers we actually need to make. The actual profit line intercepts would be identical to our answer, 60/30. So that is a complete problem taken through all the way to merit.